I'm going to draw on this axis pressure, and on the other axis I'm going to put volume. And we're going to do a little thought experiment. So I'll label it the way I usually do with milliliters, but I'm going to leave off all the numbers just to make it a little bit easier to see what's going on. So I'm not going to label the axes with numbers, but you get the idea that, of course, pressure is going to go up this way and volume is going to go up that way. Now let's say I go over to the shelf. Let's say I've got a shelf full of left ventricles, and I just grab kind of the first one that I see, and I pick it up, and it's this little guy over here. And he's empty to start out with, but I start putting some blood in him, right? He's totally relaxed. This ventricle is not contracted at all, which is important, of course, right? And I start filling it up with blood. And as I do that, I actually just kind of keep track of how much blood I'm putting in and what the pressure is inside of my left ventricle. And I notice that the pressure is rising as I'm putting more and more blood. In fact, as I really start filling this up, let's say fill it up completely with blood and try to squeeze in even more, as I keep trying to stuff it with blood, I notice that the pressure begins to rise, and now kind of rises really fast, right? So near the end, it starts rising much more quickly. And this is my curve, and I get to name it whatever I want. And so I'm going to call it the end diastolic pressure-volume relationship. Now you might be thinking, well, okay, pressure-volume relationship, that part makes sense. But why do I always have to name it end diastolic? Why not just drop those two words, right? The reason I don't drop those words is because it gives you information, right? It tells you that it's at the end of diastole that I'm doing this experiment. So for example, nobody can come by and tell me, well, was there any contraction in this left ventricle of yours? I would say no, it was completely relaxed, right? It was completely relaxed. And I can convey that information just by using the word end diastolic, because it's understood that if I'm talking about something at the end of diastole, the left ventricle must have been relaxed. And in fact, one more thing I want to point out, just because we're talking about interesting points, is that remember that if this is pressure and volume, that the pressure divided by volume, or the slope of this line, is actually equal to elastance. So if I draw the line a certain way, if I say, for example, what's going on over here, well, the slope is much higher than it is over here. Another way of saying that is that the elastance of my line is going up over time. So just keep that in mind. The word elastance actually completely makes sense to use in this context. So now we have our line or curve, and I guess one thing we can think about is what would happen if I actually, at this moment, let's say right here, this blue spot, decided to let my heart contract. What would happen if the left ventricle contracted? Well, of course the pressure would rise. I mean, that's what happens with contraction, right? But I guess the question is, what were the conditions at the moment, right? So if I say this is end diastole, right? Because of course for this situation, let's call it situation A, diastole just ended at that point. What was the volume? And let's say the volume is 125 milliliters. And let's say the pressure is 10 millimeters of mercury, right? So those are the conditions at the point where I just allowed the left ventricle to contract. Now I could choose another point. I could say, well, what about this point up here? What if I allowed contraction to happen right there? Well, that just means I waited a little bit longer, right? And let's call this situation B. And now the volume is higher, and I'm just going to say 150, even though I guess maybe it looks like my drawing kind of is a little skewed, but let's just assume that 150 is that point. And the pressure is just a smidge higher. I'm going to say it's 15 millimeters of mercury. A smidge higher, just a little bit higher. So these are the 2 points, right? A and B. So I could say, all right, well, if I want to, talk to someone about this, I could say, well, I have pressure and I have volume. And the pressure for situation A, let's go with A first, of course. A had a pressure of 10 millimeters of mercury and a volume of 125. This is how I could convey information about that spot, right? And if someone asks me about situation B, I could say, well, situation B had a slightly higher pressure and a slightly higher volume. And really what I'm giving them is information about what the conditions were at the time that contraction began, right? That's really what that point represents. Conditions when contraction began. Now you might think, okay, well, the story is done, right? I mean, what else is there to say? That was very interesting. But actually, there's another term that people use all the time, to describe the conditions when contraction begins. And the most common thing is that people get confused when this word is thrown around. The word is preload. And preload, I think it's really important to define, because sometimes people say, well, preload is pressure at the point the contraction began. And other people say, no, preload is volume when contraction began. And I'm going to say that it's neither pressure or volume, but it's something different. And I'm going to define preload as being equal to the wall stress. Well, in fact, let me actually go back one step, half a step maybe, and I'll say not even just wall stress, but I'm going to say left ventricular wall stress when contraction began. But I'm not going to say when contraction began. I'm going to use shorthand. I'm going to say at end diastole. So at the point when diastole ended, right? And in situation A and B, those are two different points we just said. The point where diastole ends, whatever the left ventricular wall stress is at that moment is preload. Okay, so that's how I'm going to define preload, and that's the way I think it's most helpful to define preload. But of course, preload has a lot to do with pressure and volume, right? It's not like it's, got nothing to do with those terms at all. Let me make a little bit of space and kind of build up my argument, see if I can try to convince you that what I'm saying makes sense. So to understand this, you got to remember what wall stress is. Remember, Laplace had this law, and he said, well, wall stress is equal to what? He said it was P, pressure, times the radius divided by 2 times the wall thickness. W is wall thickness, right? And remember, Laplace was not working with left ventricles like we are. He was working with spheres. So he was working with something that looked a little bit more like this. He was saying, okay, well, if you have a sphere, if this is your sphere, I'm going to try to draw it as best I can, right? Then if you actually take a look at the inside of that sphere, let's say you take that sphere and now I'm going to just chop away half of it. Let's say you just cut away the top half, right? Just kind of look at the midsection of that sphere. He said what you would notice is on the inside, I'm going to draw it with a white line, on the inside you've got kind of a donut. You've got something like this. And then you could actually look at it and you would see this. You would see that, okay, if you look down at it, this donut begins to look a little bit like this, right? So Laplace said if you have a situation where you have some sort of a sphere and you can actually open it up and look at it, well, then you can actually start making some interesting observations. You could say, well, from this point to this point, let's call this the radius of the inside. I'm going to call it radius in. And then from this point to this point, right here to here, I'm going to call that W, or wall thickness, we said. And then if you combine those, you get the total radius, right? So he said R total equals radius of the inside plus wall thickness, right? Something like that. And remember now that, and then of course I have to mention pressure. You might be thinking, well, where does pressure fit in all this? Pressure is just kind of what's forcing out on the walls. That's pressure. But now remember, there's a relationship, an interesting relationship between volume and radius of the inside, right? So there's volume equals 4/3 pi r cubed. And in this case, when we say r, I mean radius on the inside. So I should say r inside. And this is, I wrote lowercase r, but let me just make it really easy by just writing the uppercase r. So that's the relationship. So if you want to move things around, you can actually say, okay, well, the radius on the inside is simply the cube root of, and then you flip around all of the equation, right? You say, okay, 3 over 4 pi, and this is V for volume. And now, if you know the volume, if you have the volume information, you can figure out the radius of the inside. So we can actually do that, right? We can say, okay, what is the radius on the inside? Well, if these are the volumes, and I actually calculated this beforehand, so I wouldn't have to sit here and take the cube root of stuff while you wait patiently for me, you can actually calculate this stuff and say, okay, if I have 125 milliliters, then the radius on the inside ends up being what? It ends up being about 3.1 centimeters. And remember, you might think, well, how in the world do you get from milliliters to centimeters? remember that 1 milliliter, I'll just write here, 1 milliliter equals 1 cubic centimeter. Actually, that's nice because then when you take the cube root, you get centimeters left behind. So that's the situation A. In situation B, if I plug in 150 into this equation, right, then I get my radius on the inside becomes 3.3 centimeters. And then I could also do the next variable. I could do wall thickness. And for this, I kind of just assume, and this is kind of a fair assumption, that my left ventricle is really not going to change a whole lot from heartbeat to heartbeat, and that in general, given my size and my weight, I'm going to have a wall thickness of, let's say, about 1 centimeter, just to make the math kind of easy, right? And so then the final variable we need is the total radius, which is simply the radius on the inside plus the wall thickness. So this is just adding those two numbers together. So I can just add those very easily and say, okay, well, the total radius is just 4.1 centimeters. This will be 4.3 centimeters. And then finally, we can calculate preload now, right? You can just take all these numbers and say, okay, well, Mr. Laplace asked me for pressure. I got it right there. Mr. Laplace asked me for my total radius, and I got it right there. And Mr. Laplace asked me for my wall thickness, and I got it right there. So all the things that we need to calculate wall stress at the end of diastole, of course, that's really important, right? We have those numbers at the end of diastole. We have them, and so we can actually calculate preload, right? Which is so cool, which actually makes it, just instead of a word we throw around, it's actually something you can quantify. So let's go through it and let's calculate it. Well, let's do it first, situation A first. In situation A, I'm just going to write A now again. We have 10 times 4.1, so that's 41, divided by 2 times 1. So that ends up being, I'm just going to give you a round number. This is about 21 millimeters of mercury. So preload, another kind of interesting thing about it, it's measured in pressure units. And in situation B, we've got 15 times 4.3, again divided by 2 times 1. So that math works out to 32, right? 32. I'm rounding off. So 32 millimeters of mercury. And so you can actually see that going from situation A to situation B. And actually, let me just draw on my donut here what the wall stress is. Remember, wall stress is actually the force over area kind of pulling the heart muscle apart. And that makes sense, right? In the beginning of contraction, when the heart is about to contract, how much stress is there on the wall? That is your preload. And of course, it takes into account things like pressure and volume, of course. And you can now say to someone, well, yeah, we went from a preload of 21 millimeters of mercury right here to a preload of 32 millimeters of mercury right here. And that's actually a very rarely done calculation, but I think a very valuable one.